of zeros and 1, we can represent it with the help of 8 digit only. Okay, so for it is your for 8 bit. For 8 bit we need 2. For 16 bit we will be needing 8 different digit. Like that for 32 we need 8 different digits. Okay, so this is the convenience. So basically what will happen when we are going to discuss some issues over here, generally we are going to represent our information in hexadecimal number system for the age of representing it. But when we are going to work with a computer, it will be always in the combinations on zeros and ones, or switch on or switch off. Now, already we have said that if I am going to work with 8-bit number system, then we can represent from 0 to 255. This is the range of numbers that we can handle. But we have to work with negative numbers also. So in that particular case, what will happen? We are having 256 different representation when we talk about 8-bit number system. And what will happen? These 256 different representation or different combinations need to be divided into positive numbers and negative numbers. So in that particular case, my range is going to get reduced. So instead of 255, it will come down to some lesser number in the positive side, and remaining part we are going to put it for negative numbers. So for representing negative numbers, we are having 3 different ways to do it: sign, magnitude, form, ones complements, and twos complements. I think already you have seen these things, how to represent it. So in case of your sign magnitude form, so that most significant bit is used to represent the sign bit. 0 for positive and 1 for minus. So and remaining 7 bits is going to represent your magnitude. So now you just see we are having 7 bits for magnitude. That means the maximum number that can be represented is your 127. 7 ones is going to have 127. Okay. So that means we can go from plus 127 to minus 127. So this is 127 plus 127, total 254, plus 0 is another number, so 255. So we are having total 256 combination, but in sign magnitude form we are representing only 255 different numbers. So where is the last combination has gone? So if you look into it, then you will find that there is 2 representation of zeros. All zeros and 1 and 7 zeros. Both are going to represent 0, but one is positive 0, second one is negative 0, which is slightly meaningless because numerical value is same, it is 0. Okay. So that means we are losing one combination. To resolve it, so this is the sign magnitude representation. Now we can look into it. I am just giving the brief idea. Now similarly, already I talked about that positive 0 and negative 0. So this is the 2 combination is used for representing positive 0 and negative 0, which is equal to 0. That's why we are having 255 numbers, not the 256 number. So addition and subtraction, you know, it is from your childhood we are doing it. So if the sign is same for both the numbers, then we have to treat it handle it in different way. If they are different, sign is different, then we have to handle it different way. Okay, you just analyze those things. So now here we are having 2 other representation. One is known as your ones complements and twos complements. So when we talk about these complements, always we have to say that we are going to work with a particular range or the particular number of bits. It is an 8-bit system or it may be a 16-bit system, like that. Because this representation is going to vary if we are going to use different length. So when we are going to talk about a positive line, then we will see how negatives will be represented, and everything will depend on the size of this particular system. Okay. For 4-bit system, the representation of a negative number will be different from the representation of the same negative number in 8-bit system. Okay, so this is something you have to always remember. So it is always related to the length of the bits. So this is one complement. You just see what will happen basically. if this is one example, I'm saying, say if this is positive force, then in case of one complement, what will happen? In a simple way, you complement its speed, then you are going to get this is the negative 4. Okay. This is a simple way, but in reality, so it is not only the binary number system. With any number system, we can work with the complements. So in binary number system, it is 1's complements. Similarly, in decimal number system, we are going to have 9's complement. So in this particular case, what will happen? If we are having a number, then subtract that particular number from the maximum number that can be represented in this particular number system through with the help of that many number of bits. So what will happen here? The maximum number that we can represent over here is 1, 1, 1, 1. Okay, this is the maximum number that we can represent. Now we subtract this number, then we are going to get these things. So this is the 1's complement. Similarly, in case of 9 complements also, you can do these things. Say, if I am having 127, then what is the 9's complement of 127? This is your maximum number that we can represent with the help of 3 bits is your 999. So you subtract 127 from 999, then you are going to get the 9's complement number. Okay, so what will happen here? In this particular case, 1 will be treated as a 1's complement can be treated as a negation of the given number. Okay, this is one issue. So this is basically shows these things. How we are going to represent 0. Because again, we are having 2 representation for 0. All 0 or all 1 is basically decimal 0, and these are the 7 numbers. Just complement it 1 0 0 0. Now addition and subtraction also, you just see here what will happen basically. If to get the correct result, we have to always consider about this particular carry out. If it is carry out is 1 or these things, that we have to add it. If it is 0, we need not to add it. So this is an around carry. So this is the way we are going to do addition and subtraction. Now in 2's complements number, what will happen? Just like 1 complements, but what will happen in 2's complement, we are going to make it slightly more by 1. So whatever is there in 1 complement, we are going to add 1 to it, then we are going to get a 2's complement. So in this particular case, what will happen? 1's complements of this number is your 1 0 1 1. This is the 1 complements of the given number 0 1 0 0. Now add 1 to it, then what we are going to get? 0 0 1 1. So this is the 2's complement of this given number. So if given number is positive 4, then negative numbers will be represented by 1 1 0 0. Okay. So this is basically take 1's complements and add 1 to it. 9's complements, then add 1 to it, then you are going to get a 10's complement. Now here what will happen? You just see this is your 1 1 0 0. This is a -4 in this 4-bit number system. So if we are having an 8-bit number system, that we are going to have different representation, and this is your 0 1 0 0. So if you add these 2 numbers, then what is the result? Just see. Okay. Now you just see we are working with a 4-bit number system. So finally, result will come as all zeros. That one we should ignore because we don't have space to store it. Now you just see if when you add 2 numbers and if the result is 0, then what we say? 1 is the negation of the other numbers, because if you add +5 and -5, then only you are going to get 0. So this is the natural way it is coming, that 1 is the this 2's complement basically says that 1 is the negation of the other number. So this is positive 4, other one is -4. After adding these things, we are going to get 0. So 2's complements are used extensively in our digital system to represent negative numbers. Okay. So you just see we are adding these 2 numbers and result is 0. So 1 is negation of the others. Okay. So in this particular case, what will happen? Now you just see in sign magnitude form or in your 1's complement form, we are having 2 representation of zeros, positive 0 and negative 0. But in 2's complement form, we are just avoiding this particular negative 0. So we are going to have one extra number. You can look into it. So there is only one representation of zeros or 0. Then in positive line, we are going to have it from 1 to 7. But in negative number lines, we are going to have -1 to -8. So now, if we are going to have 4-bit number system, we can represent 16 different numbers. So these numbers will vary from -8 to +7. So all 16 combination has been used over here. Like sign magnitude and 1's complement, always we are representing 1 less. It is 15, not 16. Now, when I expand it to 8-bit numbers, then you will find that the range is represented in 2's complement number is your -128 to +127 with 0. So that means we are representing total 256 numbers. Okay. So in more generally we are going to use this 2's complement number. Now I think this is already I have explained, which is written in a slightly different way. So this is the same thing. Take the maximum number and you subtract the number, then you are going to get the 2's complement numbers and you have to add 1 to it. So this addition of 1 is taken care of here itself. So this is both the same. You just try to see and analyze it and try to get the feelings of your that complements number system. It may be 2's complements or it may be 10's complements. Like that, we can have 16's complements also. Okay. So this is related to the radix system. Now addition and subtraction. Now what will happen in case of 2's complements calculation? What will happen? Simply you can perform the addition by taking these numbers. Okay. So here you just see this is your 4 plus 3 minus 4 plus 3. These are the results that we are going to get, because you ignored about this particular bit, because we are working with a 4-bit. So 4 minus 3, this is 1. And this is your 4 plus minus 3, it is your -7. So 1 0 1 1 0 0 1 is your -7. Here you just see +7 is 0 1 1 1 and -7 is 1 0 0 1 in 2's complement. Okay, so this is the way that we can see. Now you just from here what will happen? You can do the subtraction also. Say if now here we are going to have set this 4 minus 3, then what will happen? This is -3, I are representing it. Or on the other, I can say that this is 4 minus 3, so this is a negation representation of 3. Then we can simply add them and we are going to get the result. So this is the 3 number system. Already I have told you that what are the numbers that we can represent. All right. So this is your sign magnitude, 1's complements and 2's complement. And this is the representing all the numbers of 4 bits, 3 bits number only for your convenience. So this is some overflow condition occurs. Just see, when we are going to add 5 plus 3, when we are adding 5 plus 3, my result is 8 and the combination is your 1 0 0 0. Okay, so this is the 8. Okay, but here you just see, in this particular case, this is all 1 0 0 0 is going to represent -8, not the +8. That means whatever result we are going to get, it is not correct. Okay, so that's why you have to handle this one also. And we have numbers, so it may go beyond the range that we can represent. Now say, when we are going to add 7 plus 5, this is your 12. The representation of 12 in your binary number system is your say 1 1 0 0. But when the result 1 and 0 0 will come, and if we are using a 2's complement number, then it will be always treated as your -4, not the +12. So that means the result that we have got is a wrong one, because it is a -4. So these are the situation of overflow situation, and we have to handle it properly. You have to say that whatever result you are getting, it is not correct. So this is basically, you can some examples. Already I have mentioned here. I am getting, this is after adding these two things, what I am getting, you just see, getting an error over here. Okay. So similarly here also we are getting an error. So you just analyze it and you just see when, how to identify this particular error. So this is this is a forbidden fence. So if I have to get a positive result, but if some bit pattern is coming from this particular region, then we can say that overflow has occurred. It has gone from one side to the other side. Now, how to identify the overflow? So in this particular case, overflow when carry to the sign does not equal to the carry out. So this is the way we can identify the overflow. Now you just see 5 plus 3. I am getting 8. This is basically a representation of -8, which is a wrong number. So what it says, carry in the sign does not equal to the carry out. Here said these are the carry bit 1 and 1. Addition is 0. This is the 1 is carry, 1 and 0. So 1 plus 1 0, carry is 1. Now if these two carry are different, then it is always going to indicate a overflow. So here also these two carry is different. Carrying to the sign bit. So basically it is going to indicate the sign only, 0 for positive, 1 for negative, and this is the total carry out of this particular addition. If these two are different, then always going to have overflow. And if these two are same, then we can say that there is no overflow. Whatever result we have got, this is the correct one. So -3, -5, when we are going to add it, we are going to get -8. So this is your 1 0 0 0, which is going to represent the -8. So this is the way we can handle. So this is way. Now how we are going to handle the overflow when we are going to add two numbers or subtract two numbers, and how we are going to identify overflow by looking into these two bits. That carry to the sign does not equal to the carry out. So you just see that means it is going to give me an overflow when they are different. And when they are same, no overflow. That means you just see, with the help of an XOR gate, we can always identify this, whether it is an overflow or not. So 0 and 1, the XOR gate is going to give us 1 as an output. So it is going to say that we are having an overflow. If the output is 0 of this particular gate, then we say it is your no overflow. So if I am going to use an XOR gate, and by looking into this output, we can say whether we have overflow or not. So if what will be the input? These are the two inputs, that carrying to the sign bit and the final carry out. These two will come as an input. So when they differ, then this XOR gate will give me 1 as output. That one is going to indicate that we are having an overflow. When both the inputs are same, 0 or 1 1 or 0 0, this output is 0. It says that we don't have any overflow. Okay. Now another one, how we are going to represent the real numbers. So we have seen the integers. If we are going to work with an 8-bit numbers, then what will happen? In 2's complements form, my range is from -128 to +128. Now we are having the same bit pattern. Now we have to represent the real numbers also. So for that 9.625 in binary representation, you will get that 1101.1010. Now how to represent this particular real number, so that we have to indicate the position of this particular decimal point also. So for that, what will happen? We are going to say use some notation, number system or representation, where we say it is a floating point number. That decimal point we are not going to store actually. So for that, we are having such type of representation. This is your 32-bit numbers. That most significant number bit is basically used for your sign bit. Okay, this is the sign of the number. Then we are having a bias exponent, and we are having the significant or mantissa. So basically here, what is the number that we are representing? Either sign will be positive or negative depending on this value. If it is 0, then it is a positive number. If it is 1, then it is a negative number. Then what will happen? Whatever we have stored over here, it is said a dot significant. So whatever bit pattern we have stored over here, this is the dot significant bit, okay, into 2 to the power of exponent. Here we are talking about a bias exponent, but we talk about the exponent. So here we are storing this particular exponent in a bias form, which is a positive number, but it will be converted to the exact exponent. We will see it. It is a bias exponent only. So point is actually fixed between the sign bit and the body of the mantissa. So this is the mantissa part. So here this position is fixed. So exponent indicate the place value or point position. Now let's see some example. So in this particular case, what will happen? Mantissa is stored in the 2's complement form. Exponent is in the excess of bias notation. Okay. So mantissa is always in the 2's complement form and it is in the bias notation. So bias means if we say it is a excess 128, that means what will happen? That excess value has to be subtracted from the representation. So for 8-bit exponent field, it will go, pure value will go from 0 to 255. If we say that this is excess 128, then whatever value we have, that 128 will be subtracted from this thing. So when we are storing it as 0, that means it is going to basically represent minus 128. This is the exact exponent. If we say that excess representation is 0, that means 0 minus 128, so it is 127. And when we are going to put this value as 255, then what will happen? You will get 255 minus 128. So basically we are going to say it is equal to 127. That means now my exponent can vary from minus 128 to plus 127. Okay, so subtract 128 to get it. Fine. Now, what is the, we generally, whatever mantissa part we are having, we generally normalize it. P number are usually normalized, including one number. That is, exponent is adjusted to the leading bit MSB of mantissa is 1. Since it is always 1, there is no need to store it. Since it is always 1, so we are not going to store it. So in this particular case, what will happen? In the mantissa part, we are going to store the remaining part. So for some example, I can say that if say I am going to store the number is like that 1.1010 like that. If we are going to store it, then this one we are not going to store. Okay, this remaining part we are going to store in the mantissa part. So that's why I say that 0.1010 like that we are going to store it. So now by looking into this concept, now we can try to analyze some of the situation how we are going to store it. So here we are storing say this information. How to store this information? 1.100 things into 2 to the power 1000. Okay, so in this particular case, this portion we have to store in the bias exponent. So accordingly, you convert it. So since it is a positive number, sign bit is 0. So 10100. So you have to represent it in your excess 128 notation. Then the remaining portion is 101001, and all the trailing zeros is going to have this particular significant part and exponent part. So finally, what we are storing basically, we just see we are storing basically the number 1.638 like 2 to the power 20. Now, like that, you can analyze it and you will find how we are going to storing different numbers in floating point representation. So now, what is the range over here? Already I said that it will go from 2 to the power 127, that maximum number. So it is basically around 10 to the power 77. And what is the accuracy? You can say this is, it is up to 6 decimal places. We can have the accuracy because it is 2 to the power 23. This is 2 to the power minus 23 is equivalent to your 1.2 into 10 to the power minus 7. That means accuracy can go up to 6 decimal places. Okay, now similarly we are having this particular format 750 for format. Yes.
Sir, can you repeat the last slide again? I don't know what Mantissa is clearly, and last slide, one more. In this part, why is it 10010? Like in the exponent form, it is 1.101. Why is there two zeros between?
Where is 2 zeros?
1001.
So this is you're talking about this particular part, no?
Yes, sir.
Am I right? So this is,
yes.
We are saying that this to 10100. Huh? So this is the exact value. What is this value basically? 4. It is 20 basically. Okay, 2 to the power 20. Am I right?
Yes, sir.
But we are going to store these things in excess notation. Already I have mentioned, no, this is your 128 excess. So it is 128 plus 20. That means you have to store 148. Okay, so basically what will happen? I am going to store in the excess notation 148. Okay, so minus 128. It is going to have me positive 20. Am I right? So that means to store 20, we have to store basically 148 in this particular exponent part. It is your bias exponent.
Okay, sir.
Already I have mentioned over here, no, since it is your bias exponent, then what will happen? We can go from minus 128 to plus 127. Because whatever value we are going to store, that 128 will be subtracted from this particular number. Say if you are storing 0 in exponent field, basically the exact value
minus 128.
Minus 128. Getting it? No. So that's why here also instead of 20 we have to store 148, and this is the representation of 148, I suppose. Okay. This is your 128. This is 16. Okay. You just see, try to find it out, and this is basically, oh sorry, in this particular slide it is saying that exponent is represented in minus 127. This is not 128. So here in this particular slide, instead of 148 we have to store 147. So again, this depends basically whether it is using bias 128 or bias 127. Okay, so if we mention that it is bias 127, we have to add 20 to that particular bias. So ultimately we are going to have 147, and this is basically 147. This is 128 plus 16 plus 2 plus 1. Okay, so total 147 is stored. So is it clear?
Yes, sir.
Because you have to look about this, what bias we are using actually. Okay, it may be 128 or it may be 127. So here bias 127 is used. So basically we have to subtract 127. So that's why instead of 10100, we are storing 10010011. Okay. So this is the way that we can say. Now we are having two standard. One is your 32-bit standard. Pardon? Yes.
Sir, in the same example, there we had to store mantissa in 2's complement, but the mantissa in negative and positive. So could you explain where are we using that 2's complement form?
We are, what we are saying, we are saying in the
previous slide we had discussed that we are store the mantissa in 2's complement form, but 2's complement form like not.
Say if it is your 2's complement form, already the sign is taken care by the sign bit. Okay, that means we are storing basically positive numbers only. Again, positive numbers can be represented in 2's complement form. Am I right?
Yes, sir. Sir, but in the example we have same mantissa for both positive and negative. In the example here, we have the mantissa same for.
Yeah, just try to listen to me. This is the significant part. This sign, for entire number, whatever sign bit we have, this sign bit is coming over here. Okay. Fine. This minus. So remaining part, whatever we are having, we said that now, I say that it is stored in your 2's complement form. Okay. This is the positive number representation in 2's complement form. Try to understand it. When I am using 2's complement form, positive numbers is also stored in the 2's complement form, no?
Okay, sir. Got it, sir.
Yeah, got it. No. So that's why I said that this part is in the. So what will happen here? Entire number you need not to convert it to positive numbers and then store it. It's not like that. Whatever part we are having, this part will be stored in the 2's complement form, and for positive representation, whether it is a sign magnitude form or it is a 2's complement form, representation is same. Okay.
Okay, sir. Got it, sir.
Got it.
Thank you, sir.
So this is now what will happen. We are having two formats. One is your 32-bit format and 64-bit format. Already 32-bit format, I saw the breakup. But in case of 64-bit, what will happen? We are having now 8-bit and 11-bit. So in 32-bit system, 8-bit is the exponent field. And in case of 64-bit standard, we are having 11-bit of exponent. Okay, just exponent is increasing. That means the range is going to get increased. And since we are having more number of bit pattern zeros and ones in our Mantissa field, so that means accuracy can also be improved in this particular case. You can analyze that thing. Okay. So this is the double format and single format. This is 32-bit and this is your 64-bit format. So other codes like that, we are having access code, gray code, BCD, binary coded decimal. I think all of you know about it. And if you forget it also, try to simply revise this particular code. Okay. Already we have used that access code, access 128 or access 127, whatever maybe. After the character representation, because all of you are using these things, so you know what is ASCII code, what is EBCDIC, what is Unicode. And if you slightly have some confusion, just browse through the net and try to just get some idea about this representation. Okay. So this is basically ASCII code, EBCDIC or Unicode, whatever it may be. For a particular symbols, we are having a unique bit pattern. Okay. So this is the way that we are representing. When we say that this is a character and one particular bit pattern is coming, then we will always going to say that it is going to represent one particular symbol. Maybe it is an alphabet or digit, whatever it may be. Okay, that's all for this particular course, I think, particular slide of presentation. So I thought that initially I told you that we are going to, if you will go through those particular slides, if you have some queries, then I'm going to address it. But today I have gone through the entire slides actually. So, hope that you understand the concept about why we are using binary number system, now how to represent real numbers, how to represent integers, how to represent negative numbers, and already you know about some binary arithmetic, so we are going to use all those things while going to work with the computer. So that's all from my side. If you have any question, then I can address, because time is already, we have around 10 more minutes. So if you have some queries, some question, we can discuss about it.
Sir, you said that Mantissa is stored in 2's complement. So why are we just like writing the same number bits which were written in the scientific format?
So basically, what will happen if I talk about positive plus 7? Okay, what is the 2's complement representation of the plus 7?
So we are subtracting my 128, so it's automatically 2's complement. Okay.
Got it? No. Now is it clear?
Yes, sir.
Okay, basically, so this is a positive number we are storing always in this particular Mantissa point, because the total sign is given by the sign bit. So positive numbers can be written in your sign magnitude form. It can be represented as 2's complement form. No, so whatever we are writing over here, it will be in the 2's complement form. So where it will make differences, I can again come back to this particular slide and like that say, when you are storing this particular information, okay. So now, if it is not in 2's complement form, then what will happen? It is going to represent this positive 8. Okay. But when I say that it is a 4-bit numbers and it is in 2's complement representation, then always it is going to have this particular effect actually. Okay. Okay, now I have not explicitly mentioned over here, but there are some critical cases to represent it. We will just try to find out what is the maximum number that you can represent in this particular format. What will be the bit pattern? What will happen? How zeros say? If it is 0, integer representation is one form, and in floating point representation we are going to get some other form. You just see how zeros will be represented over here. It is not like that. If all the bit patterns are 0, it is going to have the 0. So it is a 32-bit numbers. 23 plus 8 plus 1. If the contents are all 0, okay, you just see what it is going to represent. I don't think that it is going to represent 0. It will represent some other number. Okay. Now, how to handle that when we are going to store 0? How to do it? So those special cases now I am giving you as an assignment. You try to look for those particular things. Because if it is all 0, then in the significant part we are having 1.0000. And in exponent, it will not be 2 to the power 0. It will be something else actually. 2 to the power something. Because it is biased exponent. Okay, just I'm giving you some hints because if I'm doing all zeros over here, it is not going to represent 0. It is going to represent something else. So these are basically think as a reading assignments or some sort of your homework. You try to find out all those particular special cases. Go to the books, or maybe you can go to browse the net and try to identify those special cases. So if you don't have any other queries, then just a minute. So people are leaving now actually. Anyway, fine. So today I am going to give you the next your study material for the next class. So